It's good afternoon. Thanks to the organizers for putting together such a fascinating program. So the main topic I'll discuss today is joint work with Russ Lyons, Xin Sun, and with a wonderful contribution from an anonymous referee. But before starting that, I want to mention some other related work, so which I won't go into much detail, but it's related to what's discussed here. So some work with Tianyi Zheng. So I will start with that, then go to the main topic. So in general, I want to discuss relation of rate of escape of a random walk and its occupation measure, and also the classic topic of harmonic functions, which, as we heard today, is connected to entropy. So so let me start, though, with these results, which appeared a couple of years ago. So and have some background. So we're going to take a random walk on a group. So we're going to take it will be symmetric. So we're going to have this measure mu symmetric, so mu of x is mu of x inverse. The support of the measure will generate the group. And mostly, and in this part, I want to assume that it's finitely supported. Question here is to relate the return probabilities to entropy and the rate of escape and harmonic function. So this is the one theorem. So suppose we have some number gamma, and okay, so gamma should be less than a half in this statement. And suppose that the return probability, so the chance time n, that we are back at the starting point. So starting point I'll call identity. Sometimes I'll write O for the identity. But so let's assume that this is bounded by, again, up to a constant, e to the minus, well, another constant, n to the gamma. Okay, then the entropy of the walk, so the entropy of the walk at time n, so this is just the sum over all x, the probability of x, so the mu to the n is the nth order convolution of the measure, or the distribution of the random walk at time n. So we take mu to the nx log 1 over mu to the nx. Then this, right, so we have a, except here it's important, we want a lower bound on this. So have a lower bound on the transition probability, sorry. So the return probabilities, if they are at least e to the minus constant and beyond, then we get an upper bound on the entropy of, again, some constant, and and here we're going to get a gamma over 1 minus gamma. So okay, in particular, for in particular, this group with mu is Liouville. Because if gamma is less than half, then the entropy is growing sublinearly, and we know by the criterion of Avez, and then there are the improvements by Kamenovich-Vershik that this implies Liouville. There's a more precise thing. So for the latter, we don't need this strong assumption. It suffices that the return probability basically decays slower than e to the minus root n. So it suffices that this is bigger than e to the minus psi of n, where psi of n is little o of root n. So in other words, I'm assuming, let me be more precise. So we're assuming that psi of n over root n descends to 0. Psi of n should be increasing. Psi n is some function like that. Then we get Liouville. So that's.
Is it enough along the 60
Yeah, so I'm not sure right now, so I have to check that. So let me comment that the idea that one should be able to go from from estimates on heat kernel to entropy estimates was first, as far as I know, suggested by Anna Oeschler, and then there was an explicit paper on this idea by Antoine Gournay. However, so he got some other inequalities. They were already interesting, but they actually were not good enough to imply Liouville. And then a statement very close. Okay, so I should mention, write these names. So the idea was suggested by Anna Oeschler. There is a paper of Antoine Gournay that has some inequalities like this with weaker exponents, but already his paper contains some of the key ideas used in later work. Then there was a paper by Laurent Salov-Coste and Tianyi, which has very similar results to ours, just weaker with some log factors, and the proofs are more involved, but very, very similar. And this is basically polishing that work. So I won't go into the proofs of these. I will talk about the other paper, but I'll mention that key elements for this are bounds going back to Veropoulos and others, Coulon, Grigorian, who bounded transition probabilities and groups in terms of volume growth and L2 spectrum. So we use those. We actually then use some results of Romain on the stability of the L2 spectrum. And then we also use results of, I proved both with Tim Austin and results with Asaf Naor that used the idea of Markov type to bound rate of escape in groups. So I'll just mention the inequality there is 2 alpha beta less equal 1. So what is that inequality? So this is an inequality relating the rate of escape of a random walk. So you look at the expectation of dx0 xt. Suppose from in this is t to the beta. It doesn't have to scale like t to the beta, but suppose it scales like a power t to the beta, and alpha is the Guntner-Kaminker exponent of compression. It tells you how well you can compress the group into Hilbert space. So you look for a Lipschitz 1 function from the group into Hilbert space, which doesn't contract too much. So it's so points, the distance can only contract to a power alpha. So that's the alpha. So it's how much you compress into Hilbert space. And there is this relation between the Hilbert space compression exponent and the speed, 2 alpha beta less equal 1, which is proved in one paper with Naor and Austin, and then extended in some other work with Naor. And these are the elements that are used in this proof. And with these elements, the proof is not long. So, so I wanted to mention this, and we have an open problem session in the afternoon, but I'll mention one question already. What if C is exactly root n? So what if the probability decays like e to the minus constant root n? Does that imply Liouville? So we don't know that. The only kind of canonical example I know where that is the decay is lamplighter in 2 dimensions, small variations of that. And lamplighter in 2 dimensions is indeed Liouville. But whether you can infer that just from this assumption is open. So this was, I wanted to mention these results and this problem. If there are no questions, I'll move on kind of to the main part. Are there any questions on this? Okay. So the main part, it will involve some related elements, but it's kind of a very basic question. How long does a random walk spend in a ball? So again, the basic setting is we're going to look at symmetric random walks on groups. The interesting case will be super polynomial or exponential growth, not the, but still amenable. Mostly, I will look at finitely generated. So, I'm sorry, I mean finitely supported. So, again, mu finitely supported. Parts extend, certain parts are more general. And we're going to assume that this is transient. So we're not going to look at groups of growth, Z and Z, 1 or 2 dimensional, and mostly we look at super polynomial, but definitely only transient. And and here we're going to the random variable will be most interesting is the occupation time of the ball of radius r. So this is the sum. Time goes from 0 to infinity of indicator that so xt is the random walk, and we want the random walk to be in the ball around the identity. So sometimes I call the identity just O, but this doesn't mean that it's an additive group. So this is the identity. Okay, so this is the occupation time of the ball of radius r, and it should be distinguished from the first exit time. So the first time where xt is outside the ball. And question is how large can they be? So one theorem which is well known, but I mention it here. So this theorem was first pointed out in an email by Anna Erschler, and there is some another relevant email by Balint Virag, and then it's the proof in its proof and some extensions are in a paper with James Lee from 2013 that I will use some more later. But the theorem is just that the expected time to exit the ball of radius r is grows at most quadratically. And there are more precise statements, like the expected distance grows like square root of t, and so on. But this is the version of it that I will need. So let me mention that this works without the moment assumptions on mu. So here I assumed, generally I said that mostly I assume mu is finitely supported. For this statement, you don't need finitely supported and you don't need any condition. So I'm still talking about, so except, well, the support should generate the group since we're talking about, but otherwise you look at a smaller group. So, but one naive method that doesn't work to prove statements like this is to use coupling to random walk in Z or ZD. That's because there exist dead ends. So there are groups, in particular Lamplighter groups, where there are some locations where every step you take takes you closer to the identity. So this doesn't happen in Z, doesn't happen in most groups we know, but it does happen, for instance, in Lamplighter groups. So it means you cannot do a coupling argument to lattices to prove this kind of statement. So I will, in the proof part, I will recall quickly, how we prove this, how this is proved. But another method that doesn't work is to prove this via heat kernel or transition probability bounds. So, a bound of Varopoulos going back to the 70s or early 80s is that for g of exponential growth implies Pn or mu to the n of the identity is decaying like n to the 1/3. And then this is, as shown by Alexopoulos, this is sharp, for instance, for a Lamplighter group in one dimension. So and from this, it's easy to derive a bound of r cubed on the heating time, because the transition probabilities decay like e to the minus n to the 1/3. So if you take n, which is bigger than a large constant r cubed, then the transition probabilities are so small that you can just sum them over the whole ball. In fact, the same bound shows you that in the exponential case, you have, it's easy to deduce that also the occupation r is bounded by constant r cubed. Again, this is under the assumption of exponential growth.
Well,
Yes?
instead of Lamplighter, one takes something less exotic, say for the cycle group, it's also 1/3, right?
Yes, but what is exotic is a matter in the eye of the beholder.
That's what I wanted to know.
Yes. Okay. So
What's the assumption in the Herschler result?
So no assumption. So it's I'm talking just about symmetric walks, but any group, yes, exactly, any group.
For a finite group, for example.
Yeah, any. Thank you. Any infinite group, any infinite, right? Yeah. So and so. Okay, I'll mention in one word, then I'll give. So the way it's proved is in the non-amenable case, this is true with room to spare because the walk has positive speed. So the exit time is linear in the radius in the non-amenable case. Yes.
Sorry for my ignorance, but I don't understand. I just read that E tau r is always less than constant r squared, and then you give that under the condition of exponential growth is less than
what I meant, okay, let me explain. So if what I meant is that all you could deduce from the return probability is an R cubed bound. For the R squared, you need a different, so I was kind of doing the history in the reverse order. So the Veropoulos bounds go back to the late 70s, early 80s, the Veropoulos bound and the return probability. These bounds implied an R cubed, and these bounds are sharp for the return probability. Okay? Now, if you use these bounds, because the return probability is the maximum transition probability, so the on diagonal is maximum, say, for even times. So from that, you easily deduce a bound of R cubed, which was the best known until, so this email by Anna is from 2005, and this paper, it was appeared in 2013. So the sharp, yeah, sorry, so yeah. Thank you. I apologize, yes, for the confusion. So that's so these heat kernel bounds are sharp, but when you try to deduce bounds for exit times or occupation times, you get non-sharp things. Now, okay, one conjecture is that the occupation time is always bounded by R squared. Again, in infinite. So my groups are infinite, yes. So that's an open problem, and one I want to emphasize. Today, a closely related open problem is that the entropy of the random walk at time t is going to be bigger than constant root t. This is just for exponential growth, but there is. These are closely related conjectures. They're both open. Yes?
You have in mind that the quality would be only in the diffusive case, or is it false?
Sorry?
The fact that it is really proportional to R squared, is it only true in the diffusive case? Or is it
So
something
R squared means diffusive. I don't know
yes,
what.
it is diffusive.
So I'm not
you mean
sure
by
that was the
definition.
question.
No, I mean the polynomial growth. I know because
No. So, for instance, so there are many cases where it's R squared. For instance, if you have in lamplighters, it is even so lamplighters it is always R squared. So okay. So what is our theorem? This is with in the paper with Lyons and Sun. So the expected occupation time is less than a constant R squared square root log V of R, where V of R is just the volume of the ball. I should say, when I say this conjecture, I should say that it's known in many cases, in particular known for polygrowth. Okay, so the R squared bound is known for polynomial growth, so we're looking beyond polynomial growth, in particular exponential, for these conjectures. And with this in particular, so one case to think of is if you have exponential growth, or more generally e to the r to the alpha for some exponent alpha, then you get that the occupation time is going to be bounded by r to the 2 plus alpha over 2. So you see that you interpolate between the r squared and r to the 2.5. So kind of the general universal bound we can give is 2.5. I see, and it's hidden from some of you, but Okay, so we suspect it's always 2. We have it with this correction alpha over 2. So you see, even in the exponential case, it improves on the easy bound. And okay, so that's one theorem, and I will give some ideas of proofs, but to mention a second theorem, which was one of our motivations, was not just to understand the random walk, but to understand the uniform spanning forest. So if you take take a large ball, take a uniform spanning tree in that ball, and take a weak limit, you get a uniform spanning forest. So so T0 is the component of the identity or the origin in the, I should say, the wired uniform spanning forest. So to be more precise, so you take an exhaustion of your graph by finite sets. For each finite set, you glue together all the boundary to a single node. So that gives you a finite graph. You pick a uniform spanning tree in this finite graph and take a limit as the exhaustion grows. That gives you the wired uniform spanning forest. You can find the exposition of this and various other backgrounds in my book with Lyons, which is appeared a year and a half ago and is also available from his webpage. Anyway, you have the uniform spanning forest. You look at the component of the origin, and one conjecture is that this component is always at most 4-dimensional. So specifically, the conjecture is that if you look at this component intersect with B0R, this should grow at most R to the 4th. And what we can prove is R to the 4 times, again, a log of the volume to the power 3/2. Okay, so we suspect this factor. So again, this is going to give you at most a factor of R to the 3/2. We suspect this factor is not there, and in polynomial growth, indeed, you don't need this factor, and it's known that R to the 4th suffices. And the final, before going to the proofs, I want to state one more statement. So if I look at, so what is C of 0R? So if I look at this, the component of the origin, so this is an infinite tree. I intersect it with a ball, I get a forest inside the ball, because the component could go out of the ball and come back in, and out again and come back in. So if I look at this tree intersect with the origin, and now look at the component of the origin inside the ball. So this is the component of the origin inside this intersection. So T0 is a tree, but when I intersect with the ball, I get a finite forest. Now look at the component of the origin inside this finite forest. So for this, we have a very good bound. I'll write it explicitly. Expectation tau 6R squared. So the point is, this is indeed bounded by R to the 4th. So in some sense, this is the analog of exit time for the tree. So just like the occupation time, we want to look at the trajectory and intersect it with the ball. That's the analog of this object. But then if we look at the exit time, we're just looking at the first component of the walk before it first exits. So that's smaller. And when we do this for the tree, so this is the component of the origin inside this finite forest. And for that, we have a very, very good bound of R to the 4th. So these results, you can find the papers on the archive with Sun and Lyons. So if there are no questions, I want to present some idea of proofs and really one key lemma from the paper with James Lee. No questions? So first, let me quickly explain why why the expectation of tau r is bounded by r squared. So the idea goes as follows. So in the non-amenable case, we're okay because the walk has positive speed, or it follows directly from Keston's theorem. So we can assume that G is amenable. In that case, there's this theorem of Mach, also Korevar shown going back a long time, and there is a very short proof by Kleiner, and very concrete proof again in this paper with James Lee in 2013. And what this theorem says is that in the case when G is amenable, there is an equivariant harmonic embedding, so U from G to a Hilbert space, which is Lipschitz. I can take it to be Lipschitz 1. And it's equivariant. What I take from that is that if I take the random walk and I look at U of xt minus U of xt minus 1, look at this norm squared, this is look at this norm squared, even given xt minus 1, this is just some positive number. Okay, so the harmonic, wherever you are, in one step, the harmonic function has a positive chance to change by a fixed amount, but with consequence of equivariance. That's all we need. And okay, so what okay, this is the right tool rather than heat kernel bounds to bound the exit time. So how do you bound the exit time using this? So because of this, U of xt is going to be a martingale if you Hilbert space valued martingale. But what we want is to get U of xt square that. I'm sorry, take the square of the norm of that minus delta t. This is also a martingale just by orthogonality of martingale increments. So that's the usual thing we do for martingale. Look at the square and and subtract the sum of the variances. So this is also a martingale. Okay, now I want to prove this statement. So fix R, we want to prove this statement. And as I said, I want to prove this for a random walk without any moment assumptions. So first trick is, if the walk has probability to go bigger than 2R, change that. So before making this definition, modify walk so no steps outside ball of radius 2R. No steps from 0 outside this ball. So if we have, given my initial measure mu, I modify mu so that, and I bring any mass that jumps more than 2R, I bring it back to the identity. Observe that this modification can't hurt me, because if the, so we want to bound from above the exit time for the modified walk will be smaller than for the original walk. So when I make a step of bigger than 2R, I immediately, wherever I am in the ball, I will exit the ball. So I can just remove all these steps. So I can assume that all the steps are smaller than 2R, otherwise I just remove them and only increase the exit time. So we do that as a preliminary step, so we can assume, when we prove this inequality for R, we can assume this thing. Now, we just use optional stopping for this martingale. So this martingale starts at 0, and so its value at time tau r, the exit time, this expectation is also 0. Now this is bounded at the exit time. we're at most at distance 3r from the origin. And because u is Lipschitz 1, this is going to be bounded by, well, 3r quantity squared. Again, u is Lipschitz 1. So this bounds this term at the exit time. And this is just going to be delta times the expectation of tau r. Okay, so that gives the desired claim. For simple random walk, yes. For other random walk, it's different. Yes, it's just yes. Basically, it's 1 over the degree. Yeah. Okay. What do I want to do? Okay. So now, next I want to state one important consequence of this, which is very, very nice and not well known enough in the sense that I occasionally forget it. So this is the, so if I'm going to look at the occupation time up to time t, right? So this is just the sum of Sn in B of 0r, but only summed up to t. And this, an inequality proved in this paper with James Lee is that the expectation of this random variable can be bounded. Again, C's are always constant that change from line to line. So this can be bounded by a constant times r over capital R. I'll explain t, which is bounded by a constant r root t. If expectation of tau capital R is less than t. Okay, so the setting here is we draw two balls. One will be radius little r, another one will be larger radius capital R. And in some of applications, capital R will be some power like little r to the 1.5. Okay, and assume that the expectation of tau r capital R is less than t. Then there is this bound. The expected occupation time is bounded by, well, the number of steps times the ratio of the radii. Small radius over big radius. Okay, so in other words, on average, the probability you are in the, so if you run until time t, until something bigger than the exit time of the big ball, then the probability you're in this little ball is at most little r over capital R. Now this inequality doesn't assume transient, so it's also true in one dimension, and in one dimension it's sharp. Right? So in one dimension, you know, you're spreading roughly uniformly. So without, it's not assuming any transient, so it cannot be sharpened. Sharpening this using more assumptions, you know, is one challenge, I think. Okay. Now note that if we use the inequality on exit times, then we get here because right. So capital, because of the assumption that. Right, so if I choose, so to do the last step, so notice that on the right-hand side there is no capital R. So to get the right-hand side, just write R to be a tiny constant times square root of t. Then you know from this inequality that this assumption holds, and then you get this statement. Okay, so. So what? No, I'm about to. Okay, the proof will be pretty short, but not that short. Okay, so Okay, so let's prove this. Let me explain the proof of this inequality. So again, this is in that paper, but it's nicely hidden in that paper. So, so let me explain why that's true. So define a random time. So t0 is 0. And general, each time you go distance 3r, I'm going to, from the previous points, I'm going to define a new point ti. So ti plus 1 is the first time, so that the random walk has walked the distance bigger than 3r from all the previous points. Okay, so I start at 0, wait till I walk distance bigger than 3r, that's t1, then wait till I walk distance bigger than 3r. So each time that I get walk distance at least 3r from all the previous marked points, I mark a new point. Okay, so these are these ti. So again, ti plus 1 is the first time that I've walked distance at least 3r from all the previous xtj. Okay, and then I'm going to define maybe sigma I to be, so it's just going to be 0 if ti is bigger than 2t. And it's going to be the occupation time of a ball, so some t from ti to ti plus t, indicator of xt in the ball around xti of radius r. Okay, so sigmas are, I look at the occupation time of these balls. As long as I haven't passed time 2t. Yes, question?
No, I was just decipher.
Okay, so this is the occupation. So I look at some point ti, draw a ball of radius little r around it, and count the occupation time in this ball for the next capital T steps. But we stop counting if once we went past 2t. Okay? So now a key observation is, say, ti or tk is less than so b is going to be a bound on the size of the jumps. Okay. Let me, sorry, I want to state this exactly in the notation I used. So, so tk is less than the exit time of 3. Yeah, so okay, b is a bound for the size of the jumps. Okay, because so this will be okay, and this is less than tau 4r. If r is large enough. So why is this true? Because each time, if we're going to go this far, then look at we have to go, if we go distance 3r plus bk, just look each time you exit a ball of radius 3r, how far did you go? You went to at most distance 3r plus b, and you got a new point. And then around that point, wait till you exited the ball of 3r. So in other words, by the time you exited this ball, you had to have k of these different points. Okay, so this is just triangle inequality at its best. So we're going to use this inequality. So what this means is that if k is less than capital R over 4 little r, this implies that tk is going to be less than tau capital R. So if I want the probability that tk is bigger than 2t, so that's kind of the bad event over there. So this is, if this happens, it means that tau r is bigger than 2t, which is probability at most a half, because t was assumed to be bigger than the exit time of the ball. Okay, now we're almost done, so I erase these key definitions, but for t, or actually, this is really crucial. Sigma I was this occupation time right? If t was less than, ti was less than 2t, and otherwise it was 0. Now, 3t is bigger than the sum of all the sigma I, all the sigma k from 0 to infinity. Right, so these are occupation time of balls, but if we start after time 2t, then we don't count anything. And if we start before time 2t, we count at most t, and we count at most t steps on. And all these contributions are disjoint because these balls are disjoint. They cannot be in this ball and this other ball at the same time. So this just, the interval 3t has disjoint sets of this cardinality inside, although most of these summands are 0. Asaf, any? Because ti, if ti is 2t minus 3, I'm going to start an interval of length capital T at time ti. Okay, so taking in expectations of this, so 3t is bigger than the sum of the expectation of the sigma k. And now we're going to use this inequality, so we're only going to sum, instead of all, we're just going to sum from 0 to r over 4 little r. And now what is the expectation of sigma k? It's just the probability that tk less than 2t times expectation of sigma 0. Right? Because if I start before time 2t, then just because it's transitivity, I just get the occupation time of a ball. Sigma 0 is just occupation time of a ball of radius r by time t. Okay, and this gives us what we want, because this probability is at least a half by that calculation over there. So, so we end up with so I guess it's 2r. What 2r over little r times expectation of sigma 0. What? Sorry, the 4 moved. Ah, thank you. Okay, yes, that's I didn't pay enough attention to the constants. Okay, so now we're done, because moving to the other side, you get, so here we started at 3t, so expectation of sigma 0 is less than, well, some constant that we got here, whatever, 24, t times little r over capital R. And sigma 0 is exactly this occupation R of t. Okay? Okay, so in the last so we have that inequality that's written here. So in the last few minutes, let me explain at least one of the inequalities from the new paper, how we easily derive that by combining this bound and classical bounds for return probabilities. So in order, because of the time, I'm going to make a simplifying assumption. So suppose V of r is some e to the r to the alpha. So we know that the growth function can behave rather erratically, but let's just assume it's e to the r to the alpha with some constant here I won't even write down, but okay, suppose VR grows like e to the, again, some constant r to the alpha. The point of this bound is that it holds without any regularity assumption. Right, so I have right, this holds without any regularity assumption on the growth, but let's assume this regularity for simplicity. So once we have a growth function, then there is again this classical theory that gives us a bound on the return probabilities. And in general, it's some integral formula. In this case, it just says that the probability in time t to go from 0 to any point x can be bounded above by e to the minus, again, some constant, r to the, so it is alpha over alpha plus 2. Okay, so e to the minus r to the 1/3 for exponential growth, right? And this is the general form. Again, a good place is the Pitel Sal of Cost survey, have a good discussion. It's also possible to obtain this just from the discussion of evolving sets that you can find in my book with Russ. And there are many other proofs of this. There's a very nice general argument in the paper of Russ, Lyons, and Shayanov Garan based on spectral embedding, and again many nice arguments. So use this bound, and now so when we're going to bound the occupation measure, right, we want to bound the occupation measure of a ball of radius r. So we're going to take two contributions. So one contribution is the occupation time until time t, and that we can bound by r square root square root of t. So that's the bound I just proved for you using the heating times. Plus the sum for all times bigger than t. So for all times bigger than t, we just have, so we're going to just use this bound. So this volume of the ball is e to the r to the alpha. And then we have, I did something wrong here. I'm sorry. So pt of 0x, the parameter is time. So this is the bound, e to the minus t to the 1/3 or t to the, okay, so this is the transition probability. It's in terms of time. So the bound, to bound the occupation measure, we bound until time t using the bound from the paper with James Lee. And after time t, we just use a crude union bound. So take the volume of the ball times the individual transition probability. So we have sum t greater or equal capital T of this e to the minus constant t to the alpha over alpha plus 2. Now this series here is rapidly decaying, so it's basically determined by its first term. And so this suggests what t we're going to take. The t we're going to take is going to be, so that this term is going to be small. So take t to be a large constant, so I'll write a large c times r to the power alpha over 2, alpha plus 2. So again, this will be r cubed in the exponential growth case. So by taking t to be this large, but if you plug in t, which is r to the alpha over 2, this alpha over 2 will cancel, and you'll get here r to the alpha, which will cancel this thing just by taking a large enough constant. So you're going to make this thing small, and then you just have to portend with the first term. So you can get, the second term you can get small, even smaller than 1. And then the first term, r root t, just plug in this choice of t, and you get r to the 2 plus alpha over 2. Right, so square root of this gives you alpha over 2 plus 1. You add 1, and you get 2 plus alpha over 2, which is the promised bound. So remember, r squared times square root log of the volume. Okay, so you see this is rather a direct consequence. I'm out of time, but let me say that to get the bound on the spanning tree, you just use the same ideas together with Wilson's method for the probability. So the probability that the point is in the same spanning tree as the origin, you can express it in terms of random walk, and then do the same decomposition as I used here. The proof of the last statement on the component of the origin in the tree is the most delicate, but I don't have time to sketch that, so I'll thank you for your attention.
You were supposed to say something.
Are there any examples where the expected exit time and the expected occupation time are not the same order?
Any examples? No. And this is, okay, so polynomial growth, everything is understood. It's all nice, r squared. Once you're in super polynomial growth, the relation between occupation and exit is just determined by excursion. So all you need to prove to show occupation and exit are the same is the following. The number of excursions between the sphere of radius r and sphere of radius 2r is bounded in expectation. Right? So now if you have a group of exponential growth or super polynomial growth, then the ball of radius 2r is huge compared to the ball of radius r. So it seems clear that once you reach the ball of radius 2r, probability you'll ever come back to the ball of radius r should be vanishingly small. But we don't have any theorem of this type. That's what's really missing to relate these things. And the existence of dead ends shows some minefields in this. So because it kind of depends which point in the sphere of radius 2r you reach. But the points that you reach at random by harmonic measure should not be dead ends. And so you should have a small number of excursions, basically, going to. So once you go from R to 2R, the probability of going back should go to 0. But even just
Example for a point on the 2R boundary that makes you.
yeah. So I don't have 2R, but I have 1.5R. This is just the lamplighter. On the lamplighter group, there are dead ends, so points where anything, maybe it's 1 1/4 R, so the constant, but a point on the boundary, on the sphere, specific points there, where you cannot get further before you go back to the sphere of radius R and then move out. Yes?
I made the mistake that I remember looking at the space of the archive, and then there was no square root.
Yes.
There was also a reference to a heat kernel bound by Lyons and
Shayanov-Garan, yes.
so but now you didn't present this
No, I did mention, so when I mentioned that, so this inequality, so there's a big difference when the growth function is regular, where it's very classical to get this bound, than when the growth function is general. And that's where, when the growth function is general, there are various very closely related integral bounds for the return probability. And the one we use is the one by Russ and Shayanov-Garan.
But if you just plug in this volume bound instead of what you get here and optimize it, you don't get
You don't get if you do that without using this bound from the paper with James, you don't get the square root.
No, sure. But I have this inequality, and instead of b to the r to the alpha, I can just put in the volume of the ball, right? The k is still the same. Okay.
This, you need the sharp inequality of this form. So this inequality depends on the exact volume growth, and in general, it involves some, interesting integrals. So I didn't want to. I simplified here, but this is the case we mostly think about when you think of either exponential or stretch exponential.